Okay, so I'm really grateful to be presenting this result, which is a joint work with my amazing collaborators, Bernard, Vašek, Bob and Jakub. Today, we will go back to the roots and talk about Dijkstra's algorithm. It would seem that 70 years after its discovery, there isn't really much more to say about it. But today I want to convince you that the opposite is true. Concretely, I want to share with you our results that says that there is an implementation of Dijkstra which is in some sense optimal on every graph. My main aim in this talk is to explain what that means. So first I'll talk about our setup and assumptions. Then I'll talk about the notion of being optimal on every graph as formalized by universal optimality. Then I'll talk about the kind of heaps that allow Dijkstra to be optimal on every graph. Then I'll show some examples of how those heaps help Dijkstra be faster. And finally, I'll try to sketch some basic ideas of our proof. So, we are solving the single source shortest path problem. On the input we have some graph, some weights and a source node. And now the question that we should answer first is, what goal are we even solving? What is the task? Usually, the task is to compute the shortest path distances into all vertices. And this already has a lot of fast algorithms, including a recent breakthrough sub-n-log-n algorithm for undirected graphs, and many other algorithms for graphs when the edge weights are restricted. And for all we know, there could even be a linear time algorithm. So, in some sense, there isn't much for us to say. And in this talk, we are really interested in Dijkstra. So, let's solve a harder problem instead. Dijkstra has the nice property that not only does it compute the shortest path distances, but along the way, it visits the vertices in increasing order by their distance. So let's use this as our problem instead. Let's make the problem about ordering the vertices by their distance from S. Okay, so this is the problem that we are going to solve. And one more question is, in what model of computation are we? Do we have bit tricks? Do we have, are the edge weights real numbers? Are they integers? And actually, another nice property of Dijkstra is that it doesn't have any assumptions on the weights, except that they are positive. It doesn't even directly access them. It only needs to be able to compare them. And so let's make that a part of our assumption too. So formally, the model we are in is the so-called comparison addition model, where the weights are some positive real numbers, and to the algorithm they are black boxes, and it can only access them using the two operations, addition and comparison. Okay, so this is our setup. We want to order the vertices by their distance, and we have only a black box access to the weights. Now, what's nice about this setup is that it gives us an access to some information theoretic low bounds. So we can take, for example, a star with n+1 vertices, and we can see that there are n factorial possible ways of how the vertices will be ordered based on how we choose the weights. And this is good because this means that the algorithm has n factorial possible outputs, and it only learns something about the input by doing those comparisons, but every comparison only gives it one bit of information, and so it actually needs to do at least log of n factorial bits of log of n factorial comparisons to be correct. And log of n factorial is on the order of n log n, so this means we have a omega of n log n lower bound. But look, if we look at this path, which actually has the same number of edges and vertices, then actually on this path, the problem is trivial, because this path only has one possible distance ordering, namely that the one that goes from left to right. And so there is a trivial algorithm that just outputs this unique ordering and doesn't do any comparisons at all. So what this example shows is that some graphs are harder than others. And this is a general drawback of worst case analysis, because imagine that someone gives me a worst case optimal algorithm, and then I run it on paths, and then I come back to them and complain that it's slow. And what they tell me is, okay, but I'm sorry, it's slow, but you know, we have these lower bounds. It's slow because you have this star graph, and you know, you cannot do better on the star graph. And I'm like, yeah, but I don't care about the star graph. I'm running the algorithm on paths. And so why does the fact that star graphs are somehow hard does have anything to do with the algorithm being slow on paths? And so what would be nice is if we instead had an algorithm that's optimal on every individual graph. And that's a question that people in the distributed computing community have been asking as well. And they came up with a notion of universal optimality. And now we actually have universally optimal algorithms for a lot of basic problems. But interestingly, and I'm not 100% sure, but we think that our result is the first such result outside of the distributed computing setting. Okay, and so what is universal optimality? Well, informally, if an algorithm is universally optimal, it means that on every underlying unweighted graph, it's worst case optimal with respect to the weights. So to explain it more formally, let's say that I fix the underlying unweighted graph G, and then I run my algorithm on all possible choices of edge weights. I take the maximum runtime, and then I do the same for all other correct algorithms. And now if my algorithm beats all of them on G, then it's optimal on G. And if it beats them on all G's, then it's universally optimal. And this actually wasn't the full definition. This is the full definition, because I also need to allow my algorithm to be slower by a constant factor. Otherwise, the definition would never be satisfied for trivial reasons. Okay, so this is universal optimality. Now, one different way of looking at it is through the lens of parametrized complexity. We like to have algorithms that are fast on, say, planar graphs or on bounded 3-depth graphs. And universal optimality can be thought as kind of the ultimate goal, the ultimate most fine-grained guarantee that we can get. Because if I have a universally optimal algorithm, by definition, it's also optimal on planar graphs, it's optimal on bounded 3-depth graphs, and in general, it's optimal on any class of graphs that you give me. Okay, so that's universal optimality. To sum up, an algorithm is universally optimal if on every graph G, it's worst case optimal with respect to the weights. Now, what our result is that Dijkstra is universally optimal if we use it with a nice enough heap. So let's talk about heaps. To recap, a heap is a data structure for storing a collection of items. It supports inserting new items, deleting and returning the current minimum, and decreasing a value of an item. We have fast heaps that have insertion and decrease in constant time, and only deletion is logarithmic, but it also has to be logarithmic in general, because otherwise we could use such a fast heap to break the sorting lower bound. And now the thing is that this lower bound only holds in the general case, when the access sequence can be arbitrary. But what if there was some structure in the access sequence? Could we then be able to sidestep this barrier? And this is a question that people have been asking for the past 40 or so years, not only for heaps, but also for other data structures, such as binary search trees. And there are some nice examples. For example, splay trees famously have a lot of these beyond worst case guarantees. And if the dynamic optimality conjecture is true, then splay trees are in some sense optimal binary search trees for every possible access sequence. And in some sense this sounds a lot like universal optimality, but for data structures. Interestingly, there is no analogous conjecture for heaps. But nonetheless, over the years, people have still identified some nice beyond worst case guarantees that heaps can have. And so let me show you one such guarantee. So the motivation is that maybe the access sequence has a lot of temporal locality. So a lot of the accesses are accesses to recently inserted items. And we could hope that then we are somehow faster. And one way of formalizing this is the working set bound, which basically says that the cost of deleting an item, deleting the minimum, isn't logarithmic in the size of the heap, but it's only logarithmic in the age of the minimum, where age is measured by the number of operations that have elapsed since we inserted that item. And now you may or may not be convinced that this is any good. So let me show you an example. So imagine we have some operations that initially we insert some k-1 items into the heap, and those items are really large. And that then we repeatedly insert some small item and call delete min. And we do this a lot of times. If we use a regular heap, then each delete min will cost us log k, because the heap size is k. On the other hand, if we use a working set heap, each delete min will only cost us a constant, because the age of the item is constant. So on this, you can see that at least on some sequences we can perform much better if we have a working set heap. And what I find a bit surprising is that our result is that if we plug any working set heap into Dijkstra, then what we get is a universally optimal algorithm. And this is not actually technically true, because what we also need is that the working set heap has insert and decrease in constant time. And interestingly, I talked about all this previous work, and there are some working set heaps that exist, but none of them had decrease in constant time. And so what we also do in this paper is that we construct such a heap. But since this is a talk about Dijkstra, I will not talk about it anymore, but just let you know that this is possible, that this exists. Okay. So let's now move on to Dijkstra's algorithm. So let me now try to illustrate why having a working set heap can make Dijkstra faster. So first of all, if we analyze Dijkstra, it turns out that its time complexity is linear plus the cost of all the deletement operations. And here we can already see that having a working set heap can help us, because the only thing that the working set definition says is that the deletements can be smaller sometimes. And so let's illustrate this on an example graph. So we can start with a path. And now if we run Dijkstra on the path, what it will do is it will walk on this path and it will always insert an item into the heap and then delete it immediately. And so if we use a working set heap, then each deletement costs us a constant, because we are deleting an item with a constant age. But this isn't a good example, because even a good old regular, let's say Fibonacci heap, will run in constant time per operation, because the heap has size 1. So we can tweak this example by adding these square root of n vertices and connecting them to the source. And let's say that we make the weights on the edges really large. And then if we run Dijkstra on this graph, what will happen is that it will start by inserting those square root of n vertices into the heap, and then it will walk on the path as before. And this is crucial, because now if we run this with some regular heap, then since the size of the heap is now square root of n, then every deletement costs us a logarithmic amount, but the cost of the working set heap, if we use a working set heap, is still constant, because the working set definition doesn't care about what's in the heap, it only cares about the age of an element, and this is still constant. So if we sum this up, what we get is a n log n algorithm on one side and a linear time algorithm on the other side. So we got a log n factor improvement. And I hope that on this one example, you can see how having the working set heap can help us, and how it can help us leverage the locality of the graph. Okay, so let me now sketch a little bit of the proof that Dijkstra with any working set heap is universally optimal. So what we need in the proof is to somehow match the cost of the deletements to some nice low amount. And so what we do is we find some structure in the graph, and then we charge the cost of the deletements to it. How to find this structure? Well, first assume that the graph is a tree, for simplicity of explanation. Now we run Dijkstra. And we, at any given time, we pause it. And now let's look at the exploration boundary. That is, let's look at the set of the vertices that are currently in the heap. And let's say that there are b many of them. What I claim now is that this exploration boundary proves that we need to spend at least b log b time on the graph. And the proof is basically the lower bound on that we had before on the star, but only that this time it's a bit more complicated because there are some more vertices. But I claim that if we choose the weights correctly, we can achieve all the possible b factorial orderings. And thus, by the same argument, this means that we need at least b log b comparisons. And the proof is actually pretty easy, because we can simply do a proof by picture, because I can stretch the edges like this, and now I have full control over what order these b vertices will appear in. And so this is the key idea of the proof, is that we find this, we pause Dijkstra at some point, we find this exploration boundary, and to finish the proof, we then also charge some cost of some delimits to this boundary, and then we basically recursively do the same argument on the left and the right side. And it turns out that if we do this, then everything works out, and we actually are able to get a matching lower bound. And this isn't clear at all. There are some complications, so you can look that up in the paper. But I hope that you can see the high-level picture. And this is actually it. So I hope that I managed to convince you that there are still some new things that one can learn about Dijkstra. And namely that one can tap into the long-standing research into beyond worst-case data structures to get an algorithm that's optimal on all graphs. This paper isn't about breaking some benchmarks or bringing some new techniques that are really powerful. It's more about rethinking what we computer scientists take as some basic assumptions. We usually do worst-case analysis because it leads to some nice theory. And if we used beyond worst-case analysis, it would get very messy very quickly. But if there are places where beyond worst-case analysis is as nice as worst-case analysis, then I think we should identify them. And I think this is one of those places. In general, there seem to be a lot of islands where universal optimality and its cousins work really nicely. To name a few, take distributed computing, data structures, sorting-based algorithms, sequential estimation, or bandit problems. And most of these results are pretty new, so it seems like this isn't the end state, this isn't how the landscape will look like. And so for me the question is whether at some point in the future we will be able to connect some of these islands into something more meaningful, or whether all the islands will just stay the islands. And like either way, I think it's really valuable to try and apply universal optimality to different problems and different areas. And I think it's the first step on this journey. And with that, I want to thank you for your attention. And you can check out the paper and the PDF of these slides in the video description.